So I told my students that I would be more like myself, which means I'm always a bit strange in lessons. So hello and welcome to Redox and Electrode potentials. This is typically quite a difficult subject, but I'm going to try and make it as utterly simple as possible. Okay, right. Let's do electrode potentials, but first we need to do redox, because redox is really important to understand what's going on. So redox is just basically we get reduction and oxidation, and you will get, for example here, +6 goes to +3, it's gaining 3 electrons. +2 is going to +3, it's losing 1 electron. So basically the iron is losing 1, the chromium is gaining 3. And what we've done is just balance the equation to make sure the electrons are the same. But basically something is being reduced, something is being oxidized, so that's redox. Oxidation number is the number of electrons gained or lost, and the half equations are just this split into 2 halves, showing what's happening with each species, so the chromate and the iron. And you can see that you've got gaining and losing of electrons, and all we haven't done is just times this by 6 to get the electrons the same. If you times that by 6 and then combine the two, you would get this. Right. Let's move on to oxidizing and reducing agents. Now, oxidizing and reducing agents. Okay, first of all, an oxidizing agent, I'm going to do it in the simplest way possible. It causes oxidation, therefore it must gain electrons. Oxidation is losing and reduction is gaining. So if I cause oxidation, okay, I've got to gain that electron to cause that oxidation. In simple terms, the oxidizing agent gets reduced. A reducing agent, therefore, must get oxidized because it causes something to gain electrons and therefore must lose that electron itself. Shown simply in this one here, we've looked at this and then we've looked at all of these charges and you can see that the sulfate cancels. Okay, and we get our ionic equation here. Now, that ionic equation can then be split into 2 half equations. And you can see that we are gaining electrons on this one and we are losing electrons on that one. So if it's reduced, it's the oxidizing agent. If it's oxidized, it's the reducing agent. Makes sense? Okay, I hope. Now, we're going to use these terms when we're talking through the electrode potentials and things like that, and it's a good term to remember. So let's have a look at electrode potentials. Very difficult, but I'm going to try and keep it simple. So, first of all, you set up an electrochemical cell by having a solution usually with a metal, okay, and another solution with another metal, and it's the same metal as is in the solution. You connect it by a wire to a voltmeter, and then you have a salt bridge. Now let's have a look at this in a bit more detail. That one's zinc and zinc 2+. You see the metal is the same, it's in solution, and it's part of the metal itself. Next thing is, it all has to be done at the same conditions. So 298K, 100 kilopascals, 1 mole per decimeter cubed. Okay, so that means these solutions that I've got right here are 1 mole per decimeter cubed. They're 1 mole per decimeter cubed. When I measure this number that's in there, it's at 298K, 25 degrees Celsius. It's at 100 kilopascals. That's normally room temperature and pressure. Okay, so you've got it like this. You also have, and there you have your metal and your metal in solution again, and you also have your salt bridge. Your salt bridge has ions in it, which seep into each of those solutions. So why is it there? It completes the circuit essentially in a way. But what it actually does is balances the charge. So if you look over this side, you're losing electrons. So you'll need to replace those electrons with something negative. Otherwise the charge will stop flowing, because basically those electrons won't flow if there's a lack of negativity there. You need to balance it out. So that means as the electrons are gained on this side, the K will seep into that side, and it keeps the charge the same on each side, which allows the electrons to flow in and out. But you don't need to know that. You just need to know that you have to draw a salt bridge. Now, on the left, you usually have the one that oxidizes and loses electrons, and on the right, you have the one that is reduced and gains electrons. And that's how you normally draw it. Okay, so next one is, if it's oxidized, the equation will look like this. You can see it's losing 2 electrons. That means the solid is turning into the aqueous solution. On the other side, okay, you're going to have the opposite. You're going to have reduction. Okay, Now, when it loses electrons, those electrons are going to start to flow up the wire. And then they continue to be made, and they'll continue flowing up the wire. And they continue to flow up the wire and continue to be made. Okay? And eventually they flow through the voltmeter. The voltmeter measures the push of the electrons. What's the push behind the electrons? The voltage. Okay? And it measures the voltage between the two cells. So this one is pushing the electrons away, and the other one is accepting the electrons. Okay? And it will give you the difference between the two. Now, if that's the case, as I said, that's going to lose electrons, and this is going to gain electrons. It's going to lose, this is going to gain. So the one on the right always gains, the one on the left always loses. Now, if you want to know something else, which is the anode and which is the cathode, you've got a simple way of doing it as well. So the anode is the current into the device. This is your device. So the voltmeter is your device. You know the one that's oxidized is always on the left. So therefore the electrons are coming out of that and into your device, which means the one on the left is the anode. And so the one on the left is always the anode. The one that's oxidized is the anode. Now, at the same time, that means there's loads of electrons everywhere. The electrons have been released out of the atoms to turn into ions, and they're absolutely everywhere. And because they're absolutely everywhere, okay, there's an excess of electrons there. Too many negatives. If there's too many negatives, that's why there is a negative charge. Okay, then that means that if that is the anode, this one must be the cathode. And if that's negative, this one must be positive. And that's the way you do it, the simple way you do it. Okay, and as I said, the electrons are accepted in, sucked back in, gained by this half cell. So we've got a simple drawing to start off with, and this is not how you draw it in the exam, I'll show you that at the end, but this is your setup, okay, for measuring electrode potentials. Now, electrode potentials are your difference, your voltage, okay, between two half cells. Okay, we can measure that with this voltmeter and this salt bridge. Again, we'll practice that later. But first of all, how can you tell what the electrode potential is on each half cell? So I know the electrode potential overall, but how can I do it on each half cell? The answer is I do something called a standard hydrogen electrode. Standard hydrogen electrode is made of a bit of glass where you pump the hydrogen in, and you pump the hydrogen in a pressure of 100 kilopascals overall, okay? And that goes in. Now, because the hydrogen is a gas and the H plus is aqueous, hydrogen is a gas, H plus is aqueous, you don't have a solid for your electrode. On the previous example, we had a metal and their solution, which means we had the metal to be the solid for the electrode. Here, we just have hydrogen, we just have H plus. So we have to use a different electrode, and that's when we use platinum. So if we don't have a metal to use as an electrode, we would use platinum in the exam. In your schools, they'll use some graphite because they can't afford platinum. Okay, so basically the hydrogen goes in there, and then you have the H plus. Now the H plus has to be 1 mole per decimeter cubed. Okay, we'll talk about that a bit later. The standard hydrogen electrode is set to 0 volts. So it's set to 0 volts. And that means if this is 0 volts, and we know the overall is 0.34, it must mean this one is 0.34 on its own. So what we do is to measure what the half cells are on their own, the electrode potential on their own, we basically just stick it next to a hydrogen electrode, and whatever reads there is the actual electrode potential of the other half cell. Now, I'll mention this 1 mole per decimeter cubed again. If you have H2SO4 as your liquid here, to create your H+, that H2SO4 has to be 0.5 moles per decimeter cubed. That's because there's 2 protons here, it's dibasic, it's 2 protons, which means it's got double the concentration of hydrogen ions as it has to concentration of the overall acid, which means 0.5 moles of this will give a concentration of H+ of 1 mole per decimeter cubed. So that's something to look out for if they use H2SO4. So we're now going to talk about standard electrode potentials in terms of overall, but we're also going to talk about it in terms of the half cells. Each one has a standard electrode potential. Now, that has a number. And as we said when we were talking about the hydrogen electrode, we can work those out by by joining with a hydrogen electrode, because a hydrogen electrode is 0. So we can see it says 0, which means that value there is just of the copper half cell. Now they'll be presented to you as reduction in a table like this. So here is your equation, it's done as reduction, okay, and here is your cell potential for that half equation. Now, that doesn't change if you change this into oxidation. So you go that way and you lose electrons. This doesn't change to minus 0.34, really important. Now, the most important thing is that when you look at this and you compare two half cells, is that the one with the most positive cell potential gains the electrons. So the one that's most positive. So this one is more positive than that one. So this means the copper will gain electrons and it will go in that direction. The equation, okay, that will gain electrons, and the standard electrode potential in terms of, or the hydrogen electrode will lose electrons. But we're not talking about combining those at the moment. We'll talk about that later. The E cell overall electron potential between the two cells is calculated by the cathode minus the anode. So the cathode is this one, the anode is this one. Okay, always the anode on the left, the cathode on the right. But it's also the most positive minus the most negative. It makes sense, because to get this, it would be plus 0.34 minus 0. Okay, so that is the cathode minus the anode, but it's also the most positive one, which is 0.34 minus 0, which gives you overall cell potential of 0.34. Now, drawing cells. Now, there are 3 types which you might be asked to draw. It's more than likely you'll only get to do the first one, but you could be asked to do 3. So if the other electrode is a conductor, then the wire is connected to the metal, which is in a solution of the metal ion. Now, you've done that already. I've shown you that already in terms of this equation here. You can see the metal ion is in solution, and you've got a piece of that metal connected to a wire, which is connected to a voltmeter with a salt bridge. 1 mark, 1 mark, 1 mark, potentially a 4th mark. So there's quite a lot of marks in here for not a lot of work, okay? If you look at this, I've changed them. They're not in the form of reduction, just to show you what's happening. So you've got oxidized on the left, losing electrons, and you've got reduction on the right, gaining electrons. Now, if you're going to calculate the E cell for this, remember it's the most positive minus the most negative. So quickly, calculate it. Most positive minus the most negative. Now you should come up with 1.1. Okay, right. Go on to the next one, drawing cells for solutions. So we've got one normal one on the left-hand side, which is just a piece of metal in a solution. Okay, and then another one which doesn't. It has just a platinum electrode there. Okay, so if the other electrode involves a redox equation with just solutions, then you must use a platinum electrode. So there's my platinum electrode. Now this is this one here. And remember, it's 1 mole per decimeter cubed. So this should be 1 mole per decimeter cubed, what you're doing in here, right? And that means the zinc 2 plus must be 1 mole per decimeter cubed. Now, if that's the case, we have got platinum, and then we've got our manganate. Notice, when I'm saying what's in there, I'm including the H plus and the manganate. Often people get it wrong by just saying manganate and not including the H plus. You need to include both things, not the electrons, but both of the species. Right, if that's the case, we've now got a nice setup here. Okay, and we know we're losing electrons on this side because it's minus 0.76. It's the less positive number. We're losing electrons. We know we're gaining electrons on that side because it's the more positive number. We know that is the cathode, that is the anode. We know that is the positive electrode, that is the negative electrode. Okay. Right, let's move on to the last and final one. If the other electrode is a non-conductor, okay, for example, like I2, then you must use a platinum electrode and a solution of that non-conductor. Okay. So for example, we've got chloride ions here. We've got a platinum electrode, okay, and we've got platinum gas. Oh, sorry, not platinum gas, chlorine gas. So if the other electrode is a non-conductor, so that doesn't conduct, so we've got to put some platinum in there, okay? And if it's a gas, we're going to need this little setup that we've got in a hydrogen electrode to do it. So if you've got a gas and you've got an aqueous and they're both non-conductors, you're going to have to put a platinum electrode in there. And remember, that's got to be 1 mole per decimeter cubed. Okay, now, again, this is just set up according to zinc. Now, again, You can see it says 2.12 in the centre, but it might be useful for you to calculate that. So remember, it's the most positive minus the most negative. So that's the most negative, and that's the most positive. So 1.36 minus 0.76, which equals 2.12. Okay. Right, so that's your 3 examples of how you could be asked to draw it. So let's go through how to draw it. Let's do one right in front of you. So you can do any of these. So you could stop the video and you could just pick 2 of these and just calculate the cell potential, calculate the overall, and you could do your plus and your minus and your cathode and your anode and everything like that. I'd practice 2 or 3 of them, but let's show you one of them. So the things you've got to do is label the cathode and anode, okay, label the positive and negative electrodes. I want my voltmeter, I want my salt bridge, I want the standard condition stated, I want cells have half equations for each, okay, and I want to calculate the E cell and correct setup for these, and a full equation. So we'll go through all of that. It's a lot. Okay, right, so if we're going to do this now, let's go through it, get a better pen. Okay, there we go. So I want to do it with PB, and I want to do it with a hydrogen electrode. You can see it's a hydrogen electrode, it's set to 0. Okay, so my first thing is I've got to set up my voltmeter. Okay, so I'm going to set up my voltmeter right here. Okay, and all I have to do is label that as a V. Okay, and I can write voltmeter if you want. Okay, so there's your voltmeter. Then we just do a line. Okay, and we do another line like that. Okay, and then let's see if this other pen works. Okay, we know the one that is losing electrons is going to be the more negative. So the one that loses electrons is more negative, the one that gains electrons is more positive. The most negative one is the PB. So the PB is a solid, so that basically means, okay, so use that. That means we have that. That means if that's PB, so I'm going to label that as PB solid. Okay, that's going to be in a solution. Okay, and there's our solution. Right? Okay, so we've got a nice solution. Okay, and now we need to label that solution. So we label that solution, we look up here and we go, oh, PB2 plus aqueous. Okay, so that's PB2 plus aqueous. Then we look at the other side, it's H plus. Okay, we're going to need one of those funky kind of like shaped things. Okay, and then that goes down to a lovely electrode. You probably recognise that as a platinum electrode. Okay, and then my H2 is going in there, that's my H2 gas here. And then that's in a solution. Okay, and then there's your acid. Okay, and that is H plus. Okay, H plus aqueous. Okay, right, so we've got what we think is an electrode potential kind of coming together now. All right, so then, let's go from here to here. And hopefully you remember what we're calling this. We're calling this a salt bridge. Okay, so that's our salt bridge. So we're going to get a mark for this, we're going to get a mark for this, and we get a mark for all of these things too. Now, let's do it. Have we labelled the anode and cathode? Not quite yet. So the anode is where you are losing electrons, okay? I lose my electrons on the left. I already decided that at the start, that one loses electrons because it's more negative. So that is going to be our anode. Okay, so that's going to be our anode. If that's going to be our anode, that's going to be our cathode. Okay, so we've got our anode, we've got our cathode. Anode on the left, yes. Cathode on the right, yes. Label the plus and negative electrodes. Anode loses electrons, therefore that's going to be the negative. Okay, that gains electrons, therefore it's going to be the positive. Okay, voltmeter's done. Salt bridge is done. Okay, I'm very close to getting all the marks here. Standard conditions stated for both cells. Right, okay, so what I'm going to do is I'm going to put an arrow here. And I'm going to put 1 mole per decimeter cubed. 1 mole per decimeter cubed. So I'm telling you that PB2 plus is 1 mole per decimeter cubed. That is 1 mole per decimeter cubed. I'm going to say that's 298K. So that's 298K. and I want to say 100 kilopascals. So I have done all of my standard conditions. So I've done that as well. Cells have half equations for each, including all reactants and products. Okay, so the half equation for this one, I know that, I've got it up there and I've got it up there. So that's done. Okay, I don't have to write that out. Okay, calculate the E cell. Right, okay, so here's the clever bit. So what we do is we do the more positive minus the more negative. So the E cell is going to be equal to the more positive, which is 0, minus the more negative, which means it is plus 0.13. So 0.13. So there, I'm done. So I've got a mark here as well. So that's all good. Notice how many marks you can get from doing this. Well worth actually practicing. Correct setup for differing cells. Okay, so I've done my correct setup because I've got my gas here. Oh, let me just put my state symbol there. Okay. It's a good thing I checked my list because I missed that my state symbol. Right, very nice thing about this is that the electrons are the same. So the last one I'm doing is the full equation, okay? So the full equation, first of all, I need to write it in the way I want to join it together. There is something called the anti-clockwise rule, which I'll probably show you later, but I don't think you need it, okay? So the most positive one is this one. Most positive one gains. So I'm going to write that as if it gains, okay? Okay, so that's gained electrons. That what means if that gains, that must lose. Okay, so that must lose. So I need to write it like it's going to lose. Okay, so I write it like it's going to lose. Losing is going that direction. So PB, it's going to be solid. That's going to be aqueous. It's going to be gas. Okay, PB solid is going to PB 2 plus, aqueous, okay, plus those 2 electrons. Okay, those 2 electrons cancel, okay, and they cancel. Which means basically all I have to do now is write the whole thing out together. I've cancelled those 2, and that's it. Okay, so that is 2H plus aqueous plus PB solid. Okay, let's make sure I've got enough space. Always do it as reversible, okay? And then PB2 plus, okay, so PB2 plus aqueous, I've done that, plus the H2. Gas. Okay, sorry for the squeaky pen. Now, that means I've done everything. So that means I've got a mark here, I've got a mark there, I've got a mark here. Okay, I've got a mark here. I've got a mark for my charges. I could have so many marks here, it's unreal, okay? Okay, and then I've got it for that as well. So look at all those marks everywhere that I could potentially have, okay? Just for something simple. So what do you think you should do? You should practice this and write this 2-3 times with different ones, okay? Draw it out, right? Now, as I say at the end of each video, it takes a hell of a lot to make one of these videos, okay? It's a lot of time, and I really appreciate your support. So please subscribe, like, comment, okay? And please, okay, the sharing thing is the most important. Please share it so that other people can benefit from the videos, which I hope are really useful for you. Thanks.